Good evening, everyone. It is really with great pleasure to be able to welcome Andrew Kudless to UVA and introduce him as our lecturer this evening. I've known Andrew for many years. He was actually a student of mine in a 19th and 20th century history class at Tulane University many years ago. Our lecturers never want those kinds of things told, but he had written a paper that was actually one of the best in the class, which is how I remember knowing who Andrew was the first time, because when you have a class of 100 students and one student stands out, he also had long blonde hair at that time. But I remember, that was sort of a moment. But what I didn't know at that time was, of course, was the small tip of a very large iceberg, and Andrew went on to accomplish really tremendous things. I was lucky enough to have the opportunity to work with him again at CCA, California College of the Arts in San Francisco, where he is currently an associate professor and heads up the digital craft lab. Andrew has also taught at Ohio State University, where he was the Lefebvre Fellow for Emerging Practitioners. He's also taught at Yale, Rice, UC Berkeley, and the AA in London. After Tulane, Andrew did a Fulbright Fellowship in Japan. He worked as a designer for Allied Work Architecture in Portland and New York, and then he went on to the AA, the Architectural Association in London, did a post-professional master's in Emergent Technologies and Design. He worked with Ocean North and Expedition Engineering in London. And then he founded his firm and studio Matsys in 2004, a design studio exploring the emergent relationships between architecture, engineering, biology, and computation. His work at Matsys begins with the premise that architecture might be understood as a material body with its own form, growth, and behavior. Now, while many architects operating in the realm of digital design and fabrication have been content to expose the material logic of emergent behaviors by constructing diagrammatic, formal, and numerical analogs of real material systems in order to model their evolutionary potentials, Andrew's explorations really take this further by also operating on matter itself, continuing, although along an entirely different trajectory, I would say, in the tradition of people like Frei Otto and others whose understanding of material forces, properties, and behaviors evolve through careful research and an intense series of experimental material practices. Andrew's Confluence Park Pavilion in San Antonio, Texas, which I'm sure he'll show this evening, currently under construction, is his largest work to date. Is it your largest work? I just want to make sure there's not something that I haven't seen that's going up. It's a really tremendous example of this lineage, which you'll see. And at the same time, his P-Wall project that he developed for SF MoMA is also, in a very different way, part of this lineage. His studio's work ranges from speculative and built projects and installations, such as the Shellstar Pavilion in Hong Kong. In a little over a decade, he has designed and fabricated more than 50 projects that have been exhibited internationally, and many of which are in the permanent collections of some of the most prestigious institutions, including the Centre Pompidou, the San Francisco Museum of Modern Art, and the Frac Center in Orléans, France. Andrew has also been the recipient of many honors and awards, including the 2015 Acadia Award of Teaching Excellence. In addition to his keynote lecture tonight, and in collaboration with Melissa Goldman, our beloved Fab Lab Manager, and Michael Beaman, an assistant professor at the school, Andrew's leading a workshop with Michael and Melissa and with 30 of our students on designing and fabricating a pavilion on grounds to be presented as part of the university's Bicentennial campaign that's launching on October 6th. I'm sure you've seen this. That big white thing that's emerging on the North Terrace is the project. The studio is entitled The World is Flat. and it explores methods of creatively and rigorously transcoding information from the dimensionless space of software and scripting to the two-dimensional space of many industrialized sheet goods that form our building materials to the three-dimensional space of our built environment. And uses, of course, a lot of zip ties, which are the nice white things. Andrew is an amazingly talented individual and a phenomenal teacher, and we're lucky to have him leading this tremendous project. Please join me in welcoming Andrew Kudless.
Thank you so much. Thank you, Isla. That was a great introduction. As Isla said, we've known each other for a very long time, and I was also very impressed with Isla at Tulane. She was one of my favorite professors, and I feel very lucky to have had her as my mentor, from when I was 19 years old until now. And also thank you to Melissa and Michael and all of the students who have been just fantastic. I wish I always had this team kind of working with me. It's amazing to just send files, to work with the students to begin with over the first 5 days of the course, over the term, and then to be kind of sending files back and forth, and then days later seeing the structure being developed on the terrace. It's really phenomenal, and it's about halfway done, so we have a lot more to go. So if anyone wants to join, I'm sure we'd accept some more volunteers. Okay, so can we turn the lights down? Thanks. Okay, so probably a lot of you have had the question from when you tell people that you're an architecture student or an architect. People who are not architects, they often ask you, like, oh, what type of architecture do you do? Do you do offices, houses? And it's been this thing. From when I was in high school, relatives were always asking me these questions, and when I started to kind of think about how to organize my practice, and more specifically this lecture, I started thinking about how other architects I respect, and how they've organized their way of presenting their work. And there's some common themes that a lot of how we present our work to the world, let's say, how we classify it. There's the presenting it through a range of scale. Like you talk about the small projects leading up to bigger projects, or typologies, programmatic typologies, residential versus commercial, so forth, cultural buildings, or chronological, and so forth. And I've always struggled with all of these classifications in my work, in that I felt like they were extremely artificial. Not only was I not doing houses, but it seemed like that's not really like the research in any way. That it's not about program, it's not about scale particularly either. So over the last few years, I've been trying to think of a new way of classifying the work according to what I call morphotypes, which is a term borrowed from biology that attempts to group different species together based on a combination of factors. So not just kind of their form, but also the way that those forms have come into being, the materials that they're made from, the performances, and so forth. I'm not going to talk about all of these, but this is kind of at the moment the kind of 8 categories that I have. Shells, cells, fields, stacks, strands, news are the kind of ones that are more focused on my own practice, Matsys. And then eggs and totems are more focused on my academic practice. So I'm going to talk about just 4 of them today, starting with fields, and then moving on to strands, news, and then ending with shells. But before I do that, I wanted to talk about just each one of these topics, just kind of one slide each, because I find that it's not like a super clear classification system, and I think that's good. It's more that these are kind of general kind of research areas that somehow relate a concept with form, with a fabrication technique, often, and a way that something performs. But often, in any one project, I pull from different morphotypes in order to satisfy different performance criteria or different programmatic needs or many other things. So I'll kind of touch on probably all of these topics throughout the lecture, but really just focusing on 4 of them altogether. Okay, so shells. Like I said, it's although I'm calling it shells, there's really kind of an idea. It's more of like a just a placeholder, the word shells, for a much larger idea, and that idea is I'm able to work through that idea through the particular morphotype of shells. So I'm just going to read kind of these brief things from each one of them. So they're really kind of like prompts of like, these are the things that kind of are behind the research that get me kind of thinking about how, questioning my own work and trying to understand how to kind of reframe the work in different ways. So how do we integrate form, structure, and material? What can we learn from the innovative research of engineers and architects such as Heinz Eisler, Freyato, and Felix Candela, who created incredibly strong and lightweight shells? How can this research be extended into the digital realm? And just to kind of touch on this a little bit more, I mean, I'll go into shells later in the lecture, but there was, I think, this incredible body of work. Obviously, the modern movement in architecture, a huge movement, but within that, this kind of subgroup of architects and engineers that were quite dispersed. Unlike many movements within the larger modern movement, it wasn't based on a particular location. These engineers and architects were all over the world. There are other ones like Eladio Dieste, many others. But they were all kind of trying to find a more integrated approach to form and structure and performance or material. So this is the Mannheim grid shell by Freyato, which I think is just, it's one of the most incredible buildings I've ever been to. Designed, this is a 2-year temporary pavilion, and it's now been up for 40 some years. All made out of just very simple 2x2 wood. Okay, cells. So how do we work with difference and repetition? How can something be both modular and seemingly non-standard? So I'm not gonna, this isn't one of the topics that I'm gonna dive into deeply, but you'll see it kind of appear in a few of the other projects. And something, in a lot of my projects of going from kind of a completely non-standard cellular organization to something that's completely standard and module. So how do you work in that spectrum, and when is it appropriate to have something be completely non-standard versus something that is repetitive, and how do you deal with repetition aesthetically, technically, in fabrication and so forth? Fields. How has computational thinking and art informed each other? How can robotic control contribute to the production of art? And how do we relearn the generative act of drawing in the age of automation? I'm going to since this is the first topic I'm going to go into, I'm going to hold off going deeper into this for a few more slides. Stacks. How can we rethink digital design to reduce material waste? I think one of the, I'm also not going to dive into this one too much, so I'll just, with any of the specific projects, so I'll just talk a bit about it now. I think one of the side effects of digital design has been that we privilege, this is kind of a self-critique of my own work, but I think of a generation of my peers as well, that new design tools have enabled new forms, and new fabrication tools have enabled those forms to be constructed. However, in that kind of workflow, one of the things that's been kind of left out of it has been a focus on material efficiency and just the kind of the raw material and the sizes that things come in. So we're all used to, I'm sure many of the students in the room who have been helping on the project have been cutting up lots of scrap waste coming off the CNC router. And although this project is not focused on this topic at all, the particular project outside, other projects of mine have been kind of questioning that. Like that if you always start from the form, and that the form takes precedence over everything else, over fabrication and so forth, because we have the tools that can fabricate non-standard things, you kind of work yourself into this bind where you're always producing an excess of waste. So in some of my projects, I kind of tried to flip that around. Of how do you start from the size that materials come in and work towards something that's non-standard, yet that still makes efficient use of those materials. Strands. How do we move between the singular and the multiple? How do geometries and materials bifurcate, bundle, or merge? I will dive into this later, but I think it's a really important topic for me. And that within nature, because as things grow, it's quite easy to have kind of gradients between materials, to have one thing turn into two things in an almost seamless way, in the same way that like a tree branch would split, and the way that the fibers of that, the grain of the wood would kind of integrally deal with the stresses and the emergence of those branches. It's extremely hard to do that with things that are not grown. But I think it's an important concept for us to kind of deal with, both aesthetically but also technically. News. How can the world of top-down design work with bottom-up emergent systems, and how do we release control, and what do we gain from that? So, like I said, the kind of pneumatic structures, and I'm using pneumatic in a fairly broad way. It could be, it's not just things that are inflated with air, they could be inflated with many other materials. But one of the things that I've learned, and I'll talk about this later, is just how do you begin to work with systems that in some ways have their own internal logic? And when do we know to kind of back away and allow that logic to kind of proceed? And when do we know to kind of get our hands dirty and start manipulating constraints within that logic to perform things that we want it to perform? Okay, and then I'm just jump into the two quickly, the more academic kind of morphotypes. So I've been teaching a number of classes for the last 4 years that, let's just say for the first, 5 or 6 years of my teaching, I was really teaching based on what I saw around me. Learning from mentors, other professors, peers, and so forth. And I found that there was a fairly standard way, and probably many of you in this room have experienced this, that you're given a site, you're given a program, you analyze the site and program, something magical happens, and all of a sudden you have a design. And that magical moment, it's very hard and it's very mysterious what happens of where you've been studying some very rigorous data set, and then somehow you have a form. And I for years I've been kind of trying to understand that process and how to make it a little bit more apparent what's going on with student in that design process, but also how to allow other factors to enter into the design process at an early stage. I think what typically happens in a lot of student projects is that you do a lot of analysis at the beginning of the project, and then you develop kind of a design, and then in the last week or two of the term, you have to build a model, you have to figure out what it's made of, what structural system it's using, and it's just always the last thing that you're thinking of. And when you're actually practicing architecture, it's often kind of one of the first things you're thinking of. And I think the relationship we have with craft is really important. It's something that we often, I think, relegate to the very end of the design process, that we talk about like the craft of the model, at the end of the term, it needs to be well crafted. Rather than kind of thinking how a design idea might be generated out of a craft process. I didn't read this yet. How can we teach craftsmanship, and how can knowledge of craft, materials, and tools inform the design process? How do we teach the necessary and productive process of failure? I think this is another important thing, failure, that in this particular project, I had students make 5 of these 16-inch tall eggs over 4 weeks. And they basically just had to choose one material and one way of working, let's say, of like casting concrete or using the table saw. And I often said, this is an opportunity to spend 4 weeks learning a new tool. Like maybe you've never welded before, or maybe you don't know how to cast, or whatever it might be. I'm giving you free rein to become a master at this, spending all of your time for 4 weeks learning a craft. And then only at that point, when they have kind of mastered a certain way of thinking about form and material and fabrication, do I then begin to introduce sight and program and say, okay, based on these, how would you reinterpret sight and program and the possibility of a design with those two in relation to this material system that you've developed? I think it's been really rewarding for me to see because, and hopefully for some of the students, but not all of them. And I think this is important too, that sometimes I would have the students who were like, getting A's in every studio, and they'd get into my studio, and then they would not get an A because they couldn't get their head around this way of working. Or the other students who were like, kind of straight C, B students, all of a sudden would get an A. And I think it's because we have to kind of respect that there are many ways of learning, and I think too often within architecture school, we kind of have a certain pedagogy that everyone is going to learn the same way. So related to that, after doing some advanced studios dealing with the eggs, I started 3 years ago teaching the intro grad studios at CCA. And when I took that over, I wanted to kind of redo the curriculum and focus kind of similar to the eggs, but in a let's say more essential way. That these are students who have no background in architecture, they're completely new to the field. And I basically kind of asked myself, like, if, not to get too kind of religious about this, but like with a totem pole, each community is making kind of a hierarchy in some way and calling out certain gods or certain spirits that are important to that community. So I asked myself, like, if we as a community made a totem pole, like what are the important things that we need architecture students to kind of learn and to be thinking about? So I set up a series of 7 kind of topics. Some of them are paired with a material system like casting concrete or carpentry or welding or laser cutting, whatever it might be. Others are more related to acts of drawing, section drawing, axonometrics, and so forth, that pair kind of a process of making with a conceptual process. So for instance, casting is paired with figure ground or solid void, positive negative space, and so forth. Things that we've all learned at some point, in our first year of school. But to frame it as like, here's a 2-week module where you're learning a topic that you're going to use throughout your entire career, and you're also going to learn how to cast concrete. And then we just move on quickly through these 2-week modules. And that essentially at the end of the term, each student has built this kind of totem of like what's important to them within the field. Okay, so now we get to dive in deeply into a few of these morphotypes. So the first one, fields. A few years ago, maybe more than that now, 5 years ago, I began to be a little frustrated with the way I was teaching. And I'll probably mention this a few times, that my practice, my professional practice and my teaching practice feed each other. I had been teaching a lot of classes in parametric design. And at one point, I don't know, in 2010, 11, somewhere in there, I was talking to a student, and I said something about, do you know how to do this in Grasshopper? And they're like, oh, I don't know Grasshopper. I'm not interested in doing twisting towers, so I just don't want to use Grasshopper. And it occurred to me, I was like, it wasn't their fault the way that they were thinking about that. It was a failure in my own teaching, and I think in my peers' teaching, to so closely tie a particular style of architecture. And I think, partly to blame, things like even the word parametricism, or the concept of tying a style with a particular tool or a way of thinking about how to use tools. It'd be like saying, oh, I don't like to do, I'm trying to even think, like, I don't like to do modern architecture because I don't like pencils. Like, it just doesn't make any sense when you put it in those terms, right? That just because modern architecture was drawn with pencils doesn't mean there's any integral relationship between those two things. And so in order to kind of escape that trap of the cliched parametric project, and that I had been teaching for a number of years, you'd step through kind of all the iconic, here's the Swiss Re Tower, and here's the Waterloo Terminal, and so forth, by very important projects that are important to the history of parametric design, but in a way that by marrying those two things together, students began to think that these tools were only important if you wanted to do that type of work. So with Adam Marcus, another professor and friend at CCA, we started to kind of rethink the curriculum and do workshops also outside of CCA to think of another way of teaching that would be kind of, let's say, more style agnostic. That it's not about architecture anymore, that it's about just a way of working and thinking and looking at the world. So we began looking at kind of the history of art, modern art, and computer art, and seeing some kind of parallels. That there were people like Saul Lewitt and Ellsworth Kelly, Ava Hess, who were not using computers, but computation was in the air, right? That certain topics of procedural techniques, of repetition, of randomization, things like that were in some ways more possible through computation. And although they weren't using it, I think their work was informed by it, or at least that's my analysis of some of the work. That the birth of kind of minimalism and conceptual art kind of runs parallel to the birth of computation. So parallel to that, there were the scientists who had access and the ability to use computers in the 1950s and 60s and 70s, who, although didn't have any training within art, they began to see the possibility of what they could do using computation to produce art. So these are people like Manfred Moore, Edward Zajac, and Vera Moeller, who I think they've produced really incredible work that, like I said, runs parallel and I think is as important to some of the conceptual artists and minimal artists that we're much more familiar with. So in my teaching practice, I began to basically give students paintings and drawings and then say, make a grasshopper model that analyzes and enables kind of an infinite number of variations on this piece of art. Because then it just totally took it away from like, is this going to be turning into a twisting tower or not? But they were learning the mathematical, the trigonometric, all of the algorithms that they would need to do kind of anything that they wanted. But they could do, it no longer had to do with a particular style. Related to this, was I think a struggle that I've been having, I think all of us have been having in drawing, the kind of evolution of drawing within architecture. So when I was going through school, although Isla may remember this, I hated drawing, I only did models, but I eventually learned the value of drawing as a generative process. And most architects would do drawing, so they were fast, and compared to model building, which was very slow. And then drawings were used to produce models and or buildings. Now, though, with the introduction of kind of BIM, it's kind of everything has been reversed. In some way, this may not be so within school, so you may not feel this right now, but definitely within the profession, you're primarily working on digital models, and drawings are automated. You draw where you want the section cut, and the drawing is then made for you based on the wall type you've selected, and the window type, and floor, and so forth. And I think there's something strange about that, and that something that was so central to the discipline of architecture has now been, in some ways, it's like an afterthought, and it may not even be needed at some point. That more cities are accepting BIM models as what can be submitted for permits. Many fabrication tools don't require 2D drawings. They only need 3D models. So we have to kind of begin to question what the role of drawing. Is there a role for drawing still within architecture? And related to that, if we accept that drawings will be automated, how can we still use that automation and use the possibility of algorithmically created and say robotically made in physical reality drawings. So as a test for myself, I often would take examples, like I was saying, from the 50s through the 70s or so. This is actually Vera Muller, who I mentioned before. She was doing her computational work in the 60s and 70s mostly. More recently, she did this kind of wall drawing made with wool thread. But essentially, it was a drawing based on an algorithm made physical through yarn. And just as a quick how do you understand the algorithm behind a drawing, essentially, or a painting, and then embody that within a parametric model. Should be a video. Let's see. There we go. So a few years ago, I had a sabbatical and I moved to Australia to do research at Bond University in the Gold Coast, and they had just purchased a gigantic robot, like 3 meter reach, 400-pound payload capacity. And I was basically kind of assigned to teach the course and how to teach students how to use the robot. And I'd never used a robot before. I was incredibly, I've used a lot of digital fabrication equipment, but I was pretty intimidated, and I definitely didn't want to just set the students loose like with a router attached to the end of the robot, because it could be really dangerous. I could break this, $500,000 robot. So I was like, let's just try to learn how to draw together. All the students knew how to draw by hand. Let's see if it's not. Let me just go to the next slide for some reason here. So there's the robot. So actually, literally just putting a pen in the end of the router and learning how to turn the spindle off. That was an important thing. Just learning the kind of kinematic body, the behavior of the robot. That it in a sense, it has its own skeleton and muscles and its own choreography. And learning what the difference, when you're learning how to draw with a pencil, or with the computer, like you learn a certain way of working, like the keystrokes on the computer or the way to hold the pencil and so forth. And we had to kind of relearn all of those things for a new tool. This wasn't happening before the lecture. I'm not sure why it's not progressing on the videos. Actually, I'm just going to start. Sorry, you want to see my email? I think if it runs through once, it has some problems. Okay, so I did a series of 16 drawings just within the first month of arriving in Australia, just to kind of teach myself how to use the robot and how to program drawings. So a lot of these were just testing, like how do you go from a thin line to a thick line? How do you randomize the thinness of that line? How do you not get the robot to shake so much? Just kind of work through different ideas within that. I then kind of set myself kind of a bigger challenge in that this robot was on a 16-foot long track. And like I said, it had a 9, 10 foot, 3 meter reach. So I had previously been studying the Lewitt project, variations of incomplete open cubes, which for Lewitt kind of provided decades worth of material for him to research, from different drawings to sculptures and so forth. And if you know this project, it basically has a few rules that he set up for himself. That the rules were the cube had to be open, so it couldn't have 12 sides, or 12 edges, I should say. And it couldn't have any less than 3 edges that were connected. In that the idea is that if you have less than 3 edges, it could potentially be planar. It's no longer a cube. It could be part of a rectangle, but no longer part of a cube. And there could be no rotational transformation of that cube that would repeat the same pattern. So he came up with, I don't remember exactly, it was like 130 or something like that, different open cubes. And then he made many of these at various scales in steel often. So I decided, what would happen if I removed some of those rules? How big does the set become when you begin to remove those? So I wrote a small Python script within Grasshopper that would basically cycle through edges of a cube within Grasshopper and then project axonometric drawings of each one of those cubes. So this kind of alien-like looking language is really just some set of those 12 edges being projected in axonometric. And then all of those are laid out from cubes made of one edge to cubes made of 12 edges at the very end. So basically getting rid of all of the constraints that Lewitt had set up and produce every possible incomplete cube. So then I created because I had a 16-foot drawing space, I made a 4-foot by 16-foot watercolor paper drawing of all 4,096 possible cubes. I think what was interesting about this is what I learned was that, like I was saying previously, that the robot has its own body, and you have to kind of understand its body and its way of moving. And it almost looks like, like Chinese calligraphy or something like that. And the reason that it looks like that, if I didn't include the image of like a diagram of what the code is doing, but basically within the computer, these are all straight lines that have the same line weight. They're not curved lines and anything like that. And the reason a lot of these characters or these axons have this kind of style to them is that the robot, I began to realize, has very similar ways of moving as we do. That basically you can program the robot to move linearly, right? And if we as a human try to move linearly, it's very hard, right? If I try to move from point A to point B in a straight line, although mathematically you think it's really efficient, to move from point A to point B in a straight line, it's actually very difficult for a body to do that. You need to concentrate really hard, with your eyes, your brain, muscles, all of these things, trying to just move in a straight line. It's very difficult. And similarly, although surprisingly, it's also hard for a machine to do that, or at least specifically this type of machine, in that it has 6 different, or in this case, actually 7 different degrees of freedom. And you can actually tell the robot, instead of moving linearly, which is quite hard, you have to think harder, you have to go slower, all of the motors have to work harder. Just go from point A to point B, however you feel is the most efficient, basically. And it can calculate, what's the minimum amount that each motor has to move. So it's kind of think of it as like the yoga for robots. That it's just all about efficient, or Tai Chi for robots. That it's incredible to kind of see the difference between a robot moving the way we would normally think robots move, very strict kind of linear movement. But it's actually the opposite in a way, that there's a way of programming the robot and it moves incredibly naturally in a weird way. It's kind of uncanny. I then extended this, this is just one slide, for a project for Autodesk where I got out of Grasshopper because I was working for Autodesk. And they asked me, they were like, here's this robot, we have this exhibition, can you do something with the robot that somehow highlights Autodesk and robots? And I said, well, I'd love to, but you don't have any software that controls robots. And they said, well, find some way around that. So I think now they're trying, that's their new market is manufacturing, and they're kind of ignoring the consumer now. But for instance, they just, a couple of years ago, they bought Delcam, which is one of the big CNC companies. But the idea in this project was essentially to suck up all of the images from Instagram from a particular geolocation. So I gave it a longitude and latitude and wrote a script that pulls images out of Instagram from, in this case, a neighborhood in Tokyo, Omotesando. And it would pull images in and then use a very small bit of Autodesk software that they had for an iPad app called Vectorize It that vectorizes images. So then that, instead of using an iPad, it's just done through code that transforms the Instagram image into a series of toolpaths for the robot. And then this whole system is on, there's a little Arduino with this kind of belt system that after each drawing is done, the whole sheet of paper moves down and a new drawing is made and takes a picture of the drawing and reloads up to a website. And it's basically this idea of, just setting this, it's kind of like a diary, like a crowdsourced diary, visual diary of a particular neighborhood. So at the end of a 2-week period, you'd have a 300-foot long roll of as many images from that particular neighborhood as it could draw. So, as I said, Adam, Marcus, and I were thinking a lot about this way of working and thinking about how other people, other peers of ours, had been using or exploring similar ideas. So last November or so, we invited 24 architects and designers to submit. We basically gave them a brief and said you have to come up with a 25-inch by 25-inch drawing, all in black and white, that somehow is a reflection, is a new project, and is a reflection on how you deal with the world of constraints and code, and however you interpret those terms within your work. And amazingly, everyone said yes, because we only gave them like 1 month, basically, to do the drawing. And it was pretty fantastic, the range of drawings that were produced. Some drawings were made with 3D printers, robots. Some other drawings were done almost by hand. Other drawings were completely coded. Others were not at all, but dealt with the code of the actual project that was being presented, how they were dealing with building codes, zoning codes, political census tracts, many other things. So codes of styles of architecture and how those styles were embedded within building codes. So I invited myself for the exhibition as well, so I'll show you that drawing. I struggled with this drawing, but I was doing the drawing over Christmas break last winter, right after Trump was elected, right before inauguration. And obviously, the talk of the wall, the wall, it was this incredibly imposing, not built, but political and cultural concept that was just in the air everywhere, especially in California. And so I just began thinking a lot about the wall, and a wall that's in some ways like the polar opposite of the wall that Trump was proposing. Like, what if a wall wasn't about kind of dividing one body from another, but the wall had somehow grown and had subsumed an entire city and became the only thing of the city. So imagine like a medieval city that the houses and castles and everything, the shops, everything within the city had just been sucked into the wall. And the wall grew to kind of consume all of those things. So I started basically with a circle, and then began adding, broke up that circle into small segments, and then every few kind of seconds, each edge of that circle got a little bit bigger, but created a rule that the edges could never intersect each other. So after a minute or so, and you can kind of see what's happening, that very similar to like different types of coral and other like slime molds and other things, that the city basically the wall grew. And I set a boundary for the wall, otherwise it would just keep on growing. So the dashed line is kind of the invisible wall that the city has to be within. And you start to see as it hits that boundary, it just kind of starts growing now a little bit more towards the center and pushing its neighbor out of the way, and they're kind of competing for space. And at this point, roughly, I would stop the simulation before it kind of broke itself. And then I had the problem kind of on a representational level. Unlike the kind of minimalist work of that I had been doing previously, looking at the work of Lewitt and some of the early computational designers, this is like the opposite, and it's like maximal. It's like how, if you're representing a city, how would someone know it was a city without, if you didn't have the title sitting there? If it was just an image of a city, how do you know it's a city? So what I struggled with was, well, not only how do you represent a city in a drawing, an aerial drawing, how do you create all of that completely algorithmically? So I didn't have to draw anything kind of, I don't mean by hand with a pencil, but even anything in Rhino or an Illustrator. I wanted everything to be completely automated and to kind of push myself to try to represent reality as compared to represent the minimalist work, which was just it's a line as a line. But here the line had to actually represent something. So there was that problem. How do you do it algorithmically? But then there's the second problem of what do you actually represent that would clue people in that it actually is a city. So I struggled for a little bit, and I just thought, well, I just need some ideas. I need to somehow generate ideas kind of outside of myself. Like, how do I go to something else and have it generate ideas for me that would represent a city? So, like as we all do, we go to Google, and I started typing in rooftop. And then I went through the letters A through Z. And every time, whatever was the most architectural word after rooftop, so like rooftop YouTube doesn't quite make sense, but rooftop yoga in architectural terms, you can begin to spatialize what that might be. Or rooftop exhaust fan, or rooftop ice skating. Apparently there's a lot of rooftop ice skating rinks in the world. And they're all over the world, it's amazing. So I basically just set a rule. I'm going to divide the wall into 26, divide it into, I think, roughly 100-foot segments. The wall is 10 miles long, and randomize the segments, and then each segment will be assigned one of 26 different programs pulled from Google's auto-completion. So then for each one, I created a small kind of subset of the file that would then look at, for instance, I had to look up graphic standards for an ice skating rink, and what are the what's the format for an ice skating rink or for a movie theater or a yoga mat, and then deploy each one of those programs on fairly irregular, like the two swimming pools happen to be next to each other, or another swimming pool over here, that all of them are using the exact same code, but because they are being grown within a different bounding condition, they end up having a different kind of result. Okay, so the next morphotype, and again, these aren't chronological in any way, they're all kind of mixed together. So Strands. So last December, I finished this project for the champagne company Parametric for their Design Miami booth. And it was an incredible project for me. It was the first time I had worked for a brand. I guess all of us, in a way, work for brands when clients hire us. And even individual families who would hire us to do a house, that the family in some ways has a brand that they're asking you to kind of get into the brand of their family, if you want to put it in those terms. But in this case, it was very explicit, like working for a marketing department that definitely cares a lot about the history of art and architecture and design, but also somehow the installation had to reflect something on the making of champagne. So I'm going to get into this project in a little bit, but I want to kind of back up and talk about some precedents, which also relate to the project outside. So again, in Australia, I started exploring kind of these bundled in addition to the kind of algorithmic drawing and robotic drawing, I started just looking at these thin, in this case, HDP tubes that you could cut them out on a CNC router, and through both their curvature along the length of the strand, but then also forcing what should be flat, like in the computer, all of these are kind of ruled surfaces they're not flat, but they're ruled surfaces, so they can be unrolled, forcing those surfaces into a shape that has curvature in both directions. So putting actually a lot of stress on the surface of each tube created these incredibly strong, like these are maybe only 2 inches, and you could probably sit on them. They're just, they would span 8 feet with a person sitting on them. So that small little test after I left Bond and came back to the United States, my colleagues there, I developed the software, and then they used it to create this larger lighting installation for a festival in Sydney. So this was kind of the start in some way of my interest in strands. Another aspect, though, was around the same time I began to, as I was programming robots and CNC routers and things like that, I began to realize how there's just a big void within the programming of 3D printers. That typically when you use a 3D printer, you have some type of mesh or other solid surface that then gets sliced. So you're basically giving control in some ways over to this algorithm called a slicer, and that slices the form up into a bunch of horizontal layers, and you give those layers properties like how far apart they are, how fast the machine is going, and so forth. But overall, you're giving a lot of control away to that algorithm. So the idea for this project, and you'll see more images of it upstairs in the exhibition, was to, rather than starting from a form, just to be directly programming toolpaths. So there's no slicing involved, essentially. You're not starting from a three-dimensional object, you're just immediately programming, creating curves in space that become the toolpaths for the printer. So you can then print things, like I would have no idea how to make solid geometry that would produce this kind of bifurcating effect, but it's much easier to produce that just through a series of curves. So getting back to what was called the Strand Garden for Design Miami, there were 4 objects or design elements of the project. The biggest one is a series of 3 screens. There were then a series of stools that formed into benches when they'd aggregate together, a central table that was 3D printed, and then an ice bucket that was also 3D printed. So I'm just going to quickly step through each of these. So this is the plan of the booth. So I definitely encourage you to go to Design Miami if you get a chance. It's an amazing, kind of overwhelming experience for a designer. I went the year before, and you're just walking by Nakashima chair, and then a Korb chair, and a Privé chair, and it's just like every famous designer of the last 100 years. There's just amazing design everywhere you look, much denser than you'd ever see in a museum. And as I said, as a designer, and knowing that the next year I was going to have to do something in that space, I was really overwhelmed and intimidated. And overwhelmed because there's just so much to look at, and there are hundreds or thousands of people walking everywhere, and you're incredibly tired and hot, and you're in a field of chairs, and you're not allowed to sit on any of them. And so one of the first things I thought of for the installation was I need to create like a clearing in a forest, right? Like if you think about like hiking through a forest, there's just things everywhere. There's the trees and the bushes and animals and the sound, and when you get to a clearing, and there's just this moment of pause, of peace, where you just sit, you have a drink of water, and you rest, and then you move on. So that was kind of conceptually the idea for the project, where rather than open up, most of the booths had no wall. So this is like the main hallway out here. And most of the booths, they want ultimate, visibility to the potential customers for these pieces. Instead, I kind of closed off most of the wall with sheetrock and then closed off the doors in a way with these screens. So that you actually couldn't see, with the exception of at the feet, you couldn't really see into the room. And then materially, I was interested in, I visited the winery in Epernay, and just there are a number of different materials that are used within the champagne making process, from the oak that is used to press the grapes, also used in some of the racks. I'll go into some of the other materials later, but I'd used in this piece for the Pompidou Museum, it's in their collection, Chrysalis 3, I'd used this material called a micro veneer from Link, a company in Michigan, that they're able to kind of shave incredibly thin, like 1/10 of an inch thin layers of wood that they then bond with paper. And that composite between the wood and the paper allows the veneer to be much, much stronger than normal veneer. Normal veneers split really easily, but by having, it's like 3/4 of the thickness is paper, and only 1/4 of it is actually wood. It allows still for the translucency of the material, but strength at the same time. So in the Chrysalis project, everything was kind of folded and glued together. In this project, I wanted to come up with a way where these strands could, I'm kind of skipping over the Strand inspiration a little bit, but Parametric, their house, the original mansion that was the owners of the founders of the winery, they have the largest collection of Art Nouveau, private collection in the world in their house. And when the client asked me to look at their collection and look at the larger collection of Art Nouveau and to somehow pull that into the project. So when I was looking at a lot of the Art Nouveau work, from lamps, paintings, whatever, there's these strands that appear again and again as this motif. Sometimes it's a woman's hair, sometimes branches of a tree, sometimes things that are much more abstract, but there's this sense of kind of continual growth of the kind of vitality of nature, and kind of this bundling and dispersion of kind of energy within a lot of the pieces. So that's kind of where the strand kind of came in. I wanted each of the pieces to somehow become these strands that came together. So in order to make the fabrication a little bit easier, I developed this technique of these little tabs that are cut and get pulled and pushed into each other, that when lit from behind, you see the kind of dark tab behind. This is a video of how that the cutting. So this was also new to me, of how do you program a drag knife on a CNC router. So this was like a $400 piece of equipment that you can just put on the end of a normal router, and it completely changes the way that you use a router. Instead of like dealing with, not only can you cut other types of material, but just how you program it, that the knife, almost like a caster on a chair, the center of the caster is always a little bit behind the axle that it pivots around. And the same thing happens here. So you have to kind of program the tool point always like 1/8 of an inch behind where you think it should go. Anyway, that produced these small little dots that kind of run up and down the length of each strand, almost like the bubbles kind of trailing up the inside of a glass of champagne. And in addition to that, this is a time-lapse movie of about 1 minute or 2 minutes of footage, where there was a kind of a random timing for the LEDs within each one, where they were dimming and brightening, so that there was kind of a barely perceptible kind of changing of light within the space. Almost like the light coming through the leaves of a forest. And again, because I wanted people to sit and rest, I had to make functional chairs or benches. So the idea here was to create a series of concrete, very white concrete, kind of reminiscent of the white chalk that the caves at the winery were carved in. There's like 1 kilometer of caves just underneath their house in Epernay. So I wanted this like really white concrete. And for the design, again, thinking about the strands and kind of the branching of how do you go from 3 legs into 1 seat in a completely kind of integral way, where it's hard to kind of define where it goes from 3 to 1. But then on another hand, a kind of bundling of them where I went back to a tutorial that I had done with students in a lot of my kind of parametric design classes. Let me speed this up. Of how to basically create an irregular hexagon that tiles space. You can kind of see 3 of the angles have 120 degrees. The other angles can have anything, and all of them are identical forms and can tile space completely. So the idea is that you could kind of have 1 stool as a singular piece, or you could bundle them together in 3 or 4 or 10 or whatever, and that they would always kind of nest to go from a stool to a large bench. So I worked with Concrete Works in Alameda, who I had worked with before on a project I'll show you a little bit. Worked through different aggregates and really refining the recipe to kind of eventually end up with this, where it has this kind of natural chalk texture of the cave. And then we 3D milled oak tops to all of those. And then throughout the 5-day event, we just rearranged them, and people would rearrange them as needed for different things. And people just loved sitting on them and getting their pictures taken. It was pretty funny just to watch. Okay, the last 2 projects, like I said, in this were 3D printed. So, like I said earlier, that I was interested in programming the toolpaths directly for the 3D printer, and there are then performances that are possible that you wouldn't normally be able to get if you tried modeling a solid object and then slicing it. So in this case, you can see a little bit what's happening, that I'm basically alternating between kind of this S kind of shape, kind of zigzagged curve, and then 2 parallel curves. And then as the form gets further away from the top, so this is kind of a section right at the very top, as it goes down closer to the leg, those S shapes get more eccentric, and they start kind of bleeding off the edge. And then, as you'll see in the video here, they then, because of gravity and how the plastic is still hot, they then drape down and melt onto the filament below and creates this kind of 3-dimensional space frame across the surface of the piece. So it ends up like simultaneously being structural. It made the piece much, much stronger, but also this kind of aesthetic kind of surface texture that made the table kind of glisten when it was backlit. So this is kind of a view. I don't know what's going on. Touched the mouse, it went back. So it's a view on the upper left of the interior, and then there were on the right-hand side other 3D printed inserts that then held a series of LED bulbs that then could be controlled, the color and intensity and so forth of the light. And then this is the bottom there. In the center is the 3D printer. I worked with Emerging Objects in Berkeley, Ron Rael, and Virginia Sanfratello, and their massive Erector Bot, which is a 4-foot by 8-foot by 4-foot high 3D printer. So each of the smallest leg there took 45 hours to print, and the largest one took 60 hours to print. So it was about 2 weeks of printing for the table. And then that really kind of made, like the centerpiece for the room, that you're kind of surrounded by the clearing, and then there's the table in the center with then the ice bucket on the center kind of strand of that table. So the ice bucket has less to do with strands, and it kind of goes more into actually the material efficiency or material waste topic that I talked about before of stacks. Like another way of thinking about 3D printing is as a series of stacks. So the idea here, this again, I wanted to relate it to the materiality of champagne or the process of making champagne. And I had this idea, I was like, could I actually make the ice bucket out of grapes? The idea, if the champagne is like the essence of the juice of the grape, I wanted to make the ice bucket the essence of the solid part of the grape. That conceptually you have, the champagne in a bottle surrounded by ice, surrounded by the solid grape in a way. So it's kind of recreating the skin of the grape. What I was able to do, luckily I found a place in Sonoma that it's like a startup where they're trying, so I should back up. So when you're making wine or champagne, you press the grapes, all the liquid goes to make the wine or the champagne, all of the skins and the seeds of the grapes typically just gets composted and mixed into soil and already in some ways gets recycled. Sometimes there's a secondary fermentation process and other alcohols sometimes get made from some of the skins. But this one company is trying to find other uses for it. And amazingly, they're taking, it's called whole vine, and they take the seeds and separate them from each species, and they take the skins away from the seeds, separate them, they bake them, and then they take the dried matter and grind them into a flour to make gluten-free flour to bake bread and cookies and things like that. So the bottom image here, like they're not doing this anymore, but you could go to Whole Foods and you could buy Merlot flour or Chardonnay flour or whatever, and it actually tastes like the grape still, but you can bake bread from it. So I talked to them, and they donated a lot of Chardonnay. And luckily, the Chardonnay is what's used for the champagne, but it also happened to be the best material for printing for some unknown reason. So we did a few tests also with emerging objects in Berkeley. This was the first test of just small little goblets, and then had the difficult task of trying to figure out, the printer is only, 8 by 10 by 8 or something like that. The ice bucket had to be much bigger than that. So how do you print something and join it together that's still waterproof? So then each of these kind of petals that emerges from the printer, which the texture on it is kind of reminiscent of a dried grape, like a raisin. Those petals are then sealed and infiltrated with a clear resin to kind of bind the material, but also make it waterproof. And then they're glued together and resealed so that they can hold the ice and water. Okay. Moving on to the next topic of news. So this is in 2005, and I was teaching a workshop as part of a seminar at Yale with Mike Weinstock. And I was visiting Yale, and I walked by the School of Architecture there, and maybe someone in the room knows more about this. I haven't been able to find any information about this sculpture. I don't know if Paul Rudolph did it or someone else did it, but it's this amazing column that has, I'm not sure if it was how it was formed, if it was formed with fabric or some other material, but I was really interested in trying to figure out how that was made. And I began experimenting with what's called dynamic relaxation, where you basically take the edges of a mesh, turn them into kind of these digital springs, and you tell all of the springs that they want to be as small as possible. But when they try to get small, when one spring gets small, it means that the spring attached to it's getting longer. So you have this kind of tug of war that iteratively happens between every single edge of the mesh. And then at a certain point, the energy within each spring is kind of distributed throughout the whole network. And you end up with these types of surfaces. So in a really naive way, these two things combined into this project, the P-Wall project, in that I thought, if I just stretch some fabric really tight and I pour concrete behind it or plaster behind it, I'll end up with something that looks like this. And instead, I got this. It was like belly button. And this was my first week of the fellowship at OSU. It was basically my first week of full-time teaching. And I made this really kind of disgusting belly button. And I kind of quickly hid it away in my office. And I was like, okay, that was a mistake. I just need to pull the fabric tighter, or I need to put sand on one side while I'm casting the plaster on the other. And it was coming up with more and more elaborate, kind of ridiculous techniques to try to replicate what I was getting in the computer. And after 3 months of that and having no success and feeling pretty embarrassed that I was failing at what I was trying to do, I just kind of started looking at the belly button again in my office. I was sitting there and I was like, well, maybe I just need to accept its ugliness and maybe it's not ugly anymore. That there are things that happened in this that I couldn't have planned, and I don't even know how to model within the computer. And there's something interesting about that. I began to kind of respect the material forces that were in play, and to get away from the idea that you have something in the computer and then you can make an exact replica of it in reality. That there are things in reality that can happen that are much better and more interesting, obviously, than what you might be able to do in the computer. So I kind of, at the same time, became aware of the work of Miguel Fisac, a Spanish architect working in the 1930s through 1980s outside of Madrid, and began to kind of, that he was working with originally pouring concrete into canvas and then into plastic sheeting as a way to make kind of a low-cost concrete form. So you didn't have to make a wood form. You could just simply cast into fabric. You could wash the fabric, reuse it, and so forth. But also, obviously, exploring kind of the aesthetic potential of the different textures that are possible. In more detail on this project, which was a clinic for the Catholic Church, what I think is really interesting about it is that the constraints that he was putting on the fabric formwork were a cross combined with a heart, two of the symbols of the Catholic Church. So when you look at a diagram of what the constraints are in the formwork, and then you actually see the effect, I think what I found really interesting about this is this was happening in the 1970s, early 80s, at the height of postmodernism, when the facades of buildings became embedded with so much meaning and signs, that this one, again, has that, but in a very different way. There's almost more of a secret meaning, this hidden symbolism within the facade that's kind of somewhat hidden by the energy of the fabrication process. So I began trying to think how I could code a relationship between constraints on the formwork, on the fabric formwork, and an image. So rather than starting from, in this case, a drawing that is repetitive and making a series of modular constraints on the fabric, was there another way that I could basically start from an image and then add a series of points that were close, where anywhere that it was black, the points would get closer together, or the constraints would get closer together, and anywhere it was white, the points would get further away. So it was a very small kind of iterative script before Grasshopper in something called RhinoScript. And the idea, it was a fairly randomly drawn, it wasn't really, the original drawing wasn't that meaningful, other than I wanted to make sure that within any 18-inch by 36-inch panel, there was always an area, you can see it maybe down here, of kind of a low density and a high density area. And I got to these density values through iterative testing, that I knew if the points got any closer together than 2 inches, the fabric wouldn't drape enough, and you get a very, very thin and weak cast of plaster. And if the points were any further away than 8 inches, it would drape so much, there was so much load accumulating within that kind of belly that was forming, that it would often rip the constraint, the dowel would rip right through the fabric, and I'd end up with a 10-foot wide puddle of plaster on the ground. So based on those two kind of limit conditions of failing by being too thin and failing by being too thick, I could then embed that knowledge within the script. So then this is the really simple mold that there was just kind of like 3 different pieces of MDF and then color-coded different points that the dowels would go in based on which panel I was casting. The fabric formwork and the frame would go on top of that, making kind of this like circus tent form, and then pour the plaster in, and any of the fabric and the dowels that are sticking up above the kind of level line of that plaster, almost like islands sticking out of an ocean, would become holes in the surface. So what was interesting when I first put this up in 2006, people came into the gallery and they're like, wow, how many axes robot did you have mill that thing? That's crazy that how did you model that? And again, it was just like that I had no idea, I still don't really know how I would make this if I tried making it with a robot or a CNC router. There are things that, like these crevices that occur that it would almost be impossible to replicate, and it would never quite look as good. And then in 2009 for SF MoMA, I was commissioned to do a much larger wall, and they approached me and they said, could we buy the wall you've already done, and then could you just do 4 more of them to get up to the size of the wall that we need? Which I wonder if they only ask architects that. I'm not sure if a museum would ask an artist, could we have this painting, and then could you just make a bunch more of them to fill up the space? It seems like a very disciplinary question. So there were some major differences, though. I said, well, number 1, no, I don't want to do that. Number 2, I want to make it better. I don't want to do the same thing I did last time. And number 3, your space is very different. So in the original wall, it was a room a little bit smaller than this, but you're primarily looking at the wall from in elevation. Whereas at SF MoMA, it was a 45-foot long hallway that was only 8 feet wide. So you could never get back far enough to see the entire wall at one time, like this elevation shows. So primarily you're looking at it obliquely. So the idea, rather than the really hard lines of where it was thin and thick within the original one, in this case it was a much more even gradient. As you can see, this kind of black sine wave moving across the entire wall. So areas that are darker here represent thinner panels, and areas that are white at the bottom or the top represent very thick panels. So essentially, you can imagine the wall kind of undulating in section like this, where the wall is kind of overhang above you versus kind of projecting out into your legs every 12 feet. It would switch. The other issue that I had, knowing that the wall would primarily be seen obliquely, in the original wall with the rectangular panels, there's this very clear line. This is a client purchased the original wall, and this is hanging up in his house in the Castro in San Francisco. So looking at this line, knowing that this was going to be the primary way that people viewed the form, I didn't like how this kind of disturbed the sense of this rolling landscape. That you still see the tiled surface. I knew seeing it in elevation, you would always see the tile, but seeing it obliquely, I wanted to kind of hide the tile. So I began looking at other ways of forming the tiles so that you never get a continuous edge moving all the way across. So by using a hexagonal panel, we went through like 10 different iterations of different types of hexagons or other forms, diamonds and other things. And then there were 4 different shapes of hexagons, which basically I'll show in a moment, kind of expanded and contracted space when you're looking at it in elevation. The formwork was very similar. I spent a summer casting 150 of these. The lightest ones were about 70 pounds and the heaviest were 150 pounds. So the first week we got like 6 done, and by the last week we were doing like 6 a day. So we got a lot better at it, and knowing, kind of understanding the craft of, at what point will the system fail entirely if we put too much in, and the recipe for the amount of perlite and plaster and hydrocal and fibers and so forth. And then this is it in the hallway at SF MoMA, which is now demolished for the new, this hallway doesn't exist anymore. It's somewhere inside of the new Snøhetta wing. And you can see a very tight space, but that the seams in the tiles kind of disappear when seen obliquely. And then when seen in elevation, there's this sense that the wall's kind of coming out at you and then receding beyond just the kind of thicker pieces, but that because they're going from kind of this extra large width to a large to a medium to an extra small, and then kind of going back up in that octave, that there's a sense that the wall is kind of moving in and out. And again, you get these forms that, again, I'd have no idea on both the surface texture, right? Like you're getting the warp and weft of the fabric is then embedded into the plaster. And then these wrinkles and faces and things that occur were really kind of phenomenal to me. And it was always a surprise. Like even though we had each one of the 100, out of the 150, there were 4 unique pieces. So whatever that is, that there was some repetition, I should say, of the constraints, but even in 2 pieces that use exactly the same constraint system, based on where I poured the plaster to start and how many times that piece of lycra fabric had been used, and how much its elasticity had been worn out, would radically change. So every time I pull the lycra off, it was just a discovery of this new landscape. And then a couple of years later, for the 75th anniversary of the museum, they reinstalled it in a gallery that was much, well, it had a lot more space to it, so you could actually see it in elevation, but unfortunately it was 2 inches shorter in height, so I had to recast the entire top row to make them shorter. But it was nice to be able to see it in this new space with daylight. So after that project was over, I was approached by the Frac Center in Orléans, and they asked me to propose a new P-wall for their museum. And one of the problems I had was that they wanted to see renderings. And I was like, well, you understand that the project doesn't exist until it's done, if that makes sense. Like, I don't know how to represent it to you. I can show you photographs of what I've done before, but this isn't, like, I can't do a rendering because the geometry is only created in the actual act of pouring the material. They weren't buying that. So I knew I had to kind of sell the project more, and I then started thinking about how to digitally simulate it, knowing that I wouldn't get it perfect. I wouldn't get all of those little creases and wrinkles and things that I really appreciated, but I could probably get it close enough that I could begin to figure out how much it would cost, which is one thing they wanted to know. And also, just for my own good, begin to test different patterns in a way that I was never able to before without casting very heavy pieces. The other aspect I wanted to kind of innovate on this project was, well, this is the site, I should say. This is the project by Jacob and McFarlane, the new Frac Center. So it's like an existing kind of old army barracks that were then turned into a hospital that was then abandoned, that then got this new kind of insertion into the courtyard. And I'm not sure why, but the architects Jacob and McFarlane decided that there would be a very long, skinny hallway that goes from this main lobby space where you get tickets and a bookstore and so forth. There's this very long hallway that gets you all the way down to kind of the corner of the building, and only then do you start getting into the galleries. Like, you don't go directly into the galleries here. So they wanted, and the client wanted, something that would pull people's eye down that hallway and allow them to kind of know that that's where the gallery, you needed to go down that way to get to the galleries. So the other problem I had in this project was just my own physicality of like casting these pieces when they were 150 pounds. It was incredibly hard, difficult work on my body. And I needed to find a way to kind of lighten the panels and to also make them stronger. So this was it wasn't going to be, one of the first questions I had for the client was that I said, when I've done this previously for SF MoMA, they had to post a guard next to it, and the guard, it was almost a performance art. The guard would just stand there and yell at people all day because people would come into this gallery and they'd immediately want to touch it because it looks like it's upholstered. Like this looks like this soft, fluffy couch. And people, like I would go to the museum at SF MoMA sometimes and just watch people. And there was this one time where there was like a high school group looking in this space, and there was, a high school boy with way too much testosterone, and you could see him visually shaking, and he was just like, and he had his fists out, and I was like, what's up? And he's like, I just want to punch this thing. and and I was like, you really shouldn't. I'm like, it's gonna hurt you. It's solid plaster. And he just really wanted to. I was like, you really shouldn't, and he didn't, but he did end up touching it, and immediately the guard yelled at him, and it was just it was happening all the time, and I didn't mind it at all. I actually wanted it to be touched. As architects, we make work that people touch, right? Like, the architecture isn't precious in the same way that a painting might be. And when I asked the curator at SF MoMA if they could allow people to touch it, they just said, we have a flat out rule, nothing can be touched in the museum. This is like 2 rooms away from a Rothko. If people start touching yours, they're gonna start touching the Rothko. We can't set a precedent for that. So the first thing I asked the clients in France, I was like, do you see this as a piece of art that needs to be preserved like a piece of art? Or do you see this like a piece of architecture that is preserved like a piece of architecture? With architecture, something gets dirty on the floor, we mop it up. You maintain architecture, but you don't preserve it in the same way that it doesn't age like a piece of art. That time occurs in a way with architecture, and we accept that into its nature, whereas art, there's a sense that time doesn't exist. And, or at least maybe for most artists and most curators or conservators. So because I knew that it was going to be touched a lot and there wasn't going to be, or the client, they said, yes, it's definitely part of the building, this is architecture. So because I knew it was going to be touched a lot and people are going to be potentially climbing on it and who knows what, there wasn't going to be a guard there. I wanted to make it much stronger. Plaster is fairly weak material. So I wanted to try doing it out of concrete instead, but doing it out of a thin shell concrete. So only like 3/4 of an inch, 1/2 inch to 3/4 of an inch concrete. So as a test, I worked with Concrete Works, and we did rubber molds of some of the test patterns from 2009, and then would shoot a thin, like 1/8 inch layer of concrete onto the inside, and then follow that up with hand-packed fiber-reinforced concrete, and then pull off the rubber and have the cast. And every once in a while, you'd see some air bubbles and things like that. But overall, it was almost like a perfect replica of the original piece. So in some ways, it was like a perversion of the original idea where each one was completely unique and you could never do the same cast twice. Now I had the possibility of making exact copies. So in some ways, I wasn't all that interested in that, but at the same time, it alleviated a number of other issues. It made it stronger, it made it much, much lighter. Rather than 14 inches thick of plaster, it was 1/2 inch, 3/4 inch of concrete. So that meant the panels could get much bigger and become much stronger. And then using the digital tools that I had developed, I was able to then quickly develop different iterations and tiling patterns and constraint patterns to test out different ideas of what a modular system would look like. In the end, I came up with these 5 pieces that roughly had the same number of casts per panel. And you could then, basically each one could be flipped 180 degrees. So you could either have like a D panel right side up or upside down, and the whole armature system behind it, how it slid onto a piece of steel, worked in either direction. And that you could use a combination of these, that there were a 2x2, two 2x2 panels, a 3x2, 4x2, and a 5x2, and different combinations of those always added up to 11 feet. So that although it was modular, you never saw the same module, or at least you'd have to look at it for a long time. And I actually still have trouble finding exact copies within the piece. Also, the addition of just the gray concrete made it this kind of velvety texture on the surface, and there's this softness of this project that I think is better than some of the previous ones with plaster. And then really quickly, just a couple of other projects along this that I've been testing, kind of other digital simulation of just changing the way that the constraints, instead of point-based constraints, line-based constraints. I then actually did a restaurant in San Francisco using these 11-foot panels with steel cables stretched across the fabric. And then quite different from those wall projects, but similar in a way. I wanted to try to make these P-wall into a ceiling, but out of air instead of concrete. So this was for a competition that I lost. That is actually, the winner is up right now, and I encourage you guys to go see it. It's at the Renwick in DC, so not too far. Freeland Buck, the firm, won the competition, but I'll show you mine. So the idea was they have this space, the salon at the Renwick, and they have a lot of, it's the closest building to the West Wing of the White House. It's like right behind the West Wing. So a lot of political events, fundraising events, weddings, whatever happen in this space at night, but during the day it has to function as a gallery. So the constraints in the project were nothing could go below 15 feet, and you couldn't get in the way of sprinklers. It had to be up for 2 years, and it had to be assembled, or the entire project had to basically, it ended up not doing this, but what we were told was that we would have from January to the end of February to design, make, and install the entire piece. So it was a completely ridiculous schedule. All of us were complaining about it. They ended up, for the winter, it just opened a few months ago, not when it was supposed to open, like 6 months ago. So they definitely gave in. I'm happy they did that. But basically my proposal was like, what can I do with kind of pre-made things that I can all buy online and have shipped there and kind of make it all from kind of ready-made parts. And the idea was to essentially create a series of clouds with netting, where there's a net that is controlled through a series of winches controlled by a computer, and that net is pulled up and down, and then gigantic white beach balls are floating in that net. So based on different values of the winch settings, you could get cumulus clouds or cirrus clouds and these kind of stripes moving across the space, or thunderclouds if all of them are lowered in the middle, and that these winches would constantly be moving. So there's like this dynamic cloud always changing above everyone's head. And then these are images from the competition. Okay, last project, or set of projects. Let's see where I am on time. Okay, over time. I'll go fast. So the shells. I already talked a lot about the shells kind of in the beginning, and quite similar to that last project, that a lot of them were simulated with these hanging nets, upside down, and then photographs of them taken and or data taken off of them to try to understand how they would perform instead of in full tension and full compression, which I'm sure your structures classes have gone over this. So in 2011 or so, I started experimenting with Kangaroo and Grasshopper and developing kind of these tessellated surfaces that could then be, components could be unrolled and laid flat and then attached to each other to make these shells. And then simulating those within the computer with different types of nets, hexagonal nets, square nets, so forth. And then I had the opportunity, similar to this opportunity at UVA with the workshop. This was just like a 4-day workshop at the University of Minnesota in Minneapolis that we used just like a pallet of cardboard, and over 4 days kind of designed and fabricated this small shell. And then I had the opportunity to do a much bigger version of this, but it was a very short project still. Instead of 4 days, it was 6 weeks from getting the commission to the end of fabrication when it opened. This was the only photo of the site that I had. It was in Hong Kong. And it was just such a weird site photo where there's not even any sky. It's just these two mysterious people who I still don't know who they are kind of there. So I had no information on the site. The client gave me no information about what was supposed to happen. They simply said, build something. We just want people to come. I'm like, is there going to be a bar? Is there going to be music? Is there, like, what is this space for? And they're like, we're still planning it. We don't know. Just, make something. Which is a really weird, constraint or lack of constraint to have on the design process. So I'll show you just quickly the simulation. But the concept was really like, essentially what they asked me. There's a spot that they have. They want people to come to it. So really simple. So how do I do that? So the idea was to kind of create this almost like vortex where there are parts of the piece that come out and then kind of gates that bring people in. So then that mesh is subdivided and the dual of the mesh is turned into these hexagons. It's simulated, turned into kind of planar pieces that can be unfolded. I worked with David Shook at SOM Engineering to kind of analyze areas that had out-of-plane forces so that we could we just make sure that the shell was actually operating like a shell, that all the forces were kind of running within the surface of the material. And then coming up with strategies for how to unfold all of that and get everything on the right layer so that they can be folded back up and have these kind of strong, continuous pieces of material going across each joint. Realizing that this material that I was using, the coroplast, has grain to it. So just like a piece of wood, it operates in one way differently than in another way. It's stronger in one direction than in other, which meant that I had to orient all of these pieces on the laser cutter so that the grain of the plastic was running in the same direction as the forces running through the surface. Nesting all of that, coming up with ways to label all of that, which is something that we'll be talking about tomorrow with the workshop with the students of how do you kind of automate drawings and fabrication drawings, diagrams, and so forth. And then it was built over a 2-week period in Hong Kong. Okay, so the last project on shells. So I was invited to be part of a team with Lake Plato Architects in Texas for Confluence Park. And I was living in Australia at the time, and I flew to do a charrette in San Antonio for this project. It was a park that was devoted to the conservation of water. So it's not a park that you'd go and like play soccer at or baseball at or something like that. It's a park that you would school trips go, and there are park rangers there that then teach children about the life cycle of water. So it was a very, very fast charrette, and at the end of the charrette, I came up with kind of a shell structure. And the problem, then everyone loved it. I went away back to Australia, thought about it for another month, and then went back to the client and said, I really don't like the design I came up with. Something that you said to me in the meeting really stuck with me, and I think we need to change the design, because what you said was that this is the type of park, the client said, he's like, I know this is going to sound crazy, but I want this to be the type of park that when it rains, you come out of your house, get in your car, and you drive to the park, because it's so cool to see rain in this park. The whole park is devoted to the flow of water and the importance of water in the Texan landscape. So the park will only really become activated when it's raining. So when I was thinking about that typically the way that architects deal with water is that we want to get the water away from the building as fast as possible. It's a big shed, and we shed the water away. And I began thinking about how other things deal with water and the collection of water. So a lot of plants, the way that they kind of capture water and bring the water down to their root system, I thought was a very different understanding of the importance of water. That it's not something to kind of shed away, but it's something to kind of bring in close and to celebrate. So essentially the concept is to create a series of these funnels. So then the problem became, how do you organize these funnels, and how do you fabricate them? So how do you arrange them on the site was the first issue. So as I began looking at different types of grids, and you can kind of imagine like a funnel either being in the center of each triangle or at the nodes, doesn't really matter. But in any of these cases, I knew it had to be a modular system, and the problem was I knew it had to be modular, and that it's easier and cheaper to make lots of the same thing than it is to make lots of different things. So the problem was that if you arrange them in a grid, when you're underneath of this shell, it's a very regular system, and it becomes kind of monotonous. Like unlike a forest where the placement of the trees is somewhat random, it would be like being in a grid of columns, and it feels very strict, and it was something we wanted to avoid. So I came up with using this kind of irregular pentagon that, when kind of flipped around in various ways, forms these larger hexagons, and each one of these pentagons is then broken down into a series of triangles, and there's only 3 different types of triangles: a C, which is equilateral, and then an A, which is asymmetric, but it is the mirror image of B. So essentially there were just kind of 2 pieces of geometry, and one of them gets mirrored to create the third. And then selecting certain ones of those within that overall tessellation, we came out with roughly, I think it was like 9 A's, 9 B's, and including some mini pavilions that we did, 10 C panels. So roughly the same number of times that we would have to cast each one, making kind of efficient use of each form. So then, just as a test to make sure that they were performing the way I wanted them to perform in relation to the flow of water, within Grasshopper, created a small script that then simulates the flow of water on a surface, so that a water droplet, when it hits a surface, always goes in the most downhill direction. So essentially, a little particle would hit the surface. It would analyze which is the most downhill vector, would go in that direction for a fraction of an inch, would then analyze again which is the new downhill direction, and so forth, so that you could begin to see how the water would then flow down and form these valleys at the center of each column. The idea being that people would be able to get into the center of these columns, and it would just be like this waterfall running down into the middle. This is the overall site plan. So you can see the pavilion here. Number 2 here, there's a classroom building that Lake Flato is mainly responsible for. That's kind of bermed underneath of the earth with solar power on top of it. There's also restrooms in there. And then the rest of the park is a series of different ecotypes from different surrounding regions of the San Antonio area, from the West Texas desert to grasslands, oak savannas, and so forth. And then it's called Confluence Park because the confluence of the San Antonio River and San Pedro Creek is right at the bottom of this bluff here, which you can see here. So it's like an extension of the Riverwalk, which, if you've been to San Antonio, is an amazing kind of public space that extends now, I don't know how, like 10 miles from north of the city to south of the city by all of the historic missions. So you can see this is the main pavilion with the 3 mini pavilions that provide shade as the school groups move from different educational station to the next. And then you can see this is a view from the confluence of the 2 rivers, so the creek and the river, up to the pavilion. And then the pavilion itself, which is used for the student groups, but also will be used for performances and weddings and who knows what else. What I think is interesting about the project is that it's all repetitive. There are only 3 unique parts in the whole piece. And only 2 parts, basically either a C and a C panel or an A and a B panel, touch each other at a hinge. There are 2 hinges at the top of each half arch, or at the top of each arch has a pin joint. And then each arch is not connected to its neighboring arch, which was surprising to me, but the engineers, AEC Collaborative in Austin, basically realized that it's much simpler to design a simple arch rather than putting arches together, because if one of them starts differentially settling or moving, and it will start kind of knocking over the arch next to it. But if you leave them completely separate, it's actually better structurally. You can make the concrete much thinner and use less rebar. And then here's kind of the last rendering of a rain event and how the water kind of comes down that funnel and allows children and adults to play within and celebrate the water. A little bit into the fabrication. Interestingly, the contractor was the one kind of most resistant to the way that it could be built. They wanted to go with a traditional formwork company and build the entire formwork for each panel out of wood. I argued that it wouldn't be very durable, and we have to take 10 pulls off of every mold, and it would be very hard to get the wood to be accurate because you'd be kind of CNC milling some type of ribs and then laying plywood on top of those ribs and building up to the finished surface. Whereas if we used fiberglass, we could mill foam and lay the finished surface directly up against that foam, so it would be highly accurate. So they got a quote for the first doing the traditional route of making formwork, and it was more expensive than the entire project budget, which I thought I was going to be fired because, like, formwork gets thrown away after it's used. So to have something that's being thrown away be the thing that costs more than the entire building, I knew it was going to be a problem. So we then got a quote from Chrysler and Associates, and it was like 1/10 of the cost of the original quote. And so I was like, look, it's stronger, it's more accurate, and it's a lot cheaper. And they decided to go with Chrysler. So the way it's built is there's foam is milled out, the fiberglass is put down, and then 2-inch thick balsa wood is laid down on top of the fiberglass, and then another layer of fiberglass is put on top of that to make like a kind of this monocoque hull, like almost like a ship's hull, that's very strong on the outside and then very lightweight on the inside, separating the two strong layers. The fiberglass panels were then shipped to Texas in 3 parts. They were bolted back together again, and then they're cast in this kind of, eventually they're going to be in this position, but they're cast in this position with the top being open. And part of the reason for that is to reduce the amount of formwork, so it cost less. But it was also, going back to that image of the water flow diagram, I thought I was going to be fired for this too, but I asked if the top surface of the concrete could be broomed in the pattern of the simulation of the water flow. So that's what that guy is doing right there with that really long broom. So the top surface is really rough and has these kind of channels that water will run along and gather dirt and pollen and pollution and whatever, and it'll age over time because of that rough texture, where the underside will be smooth. And then each panel is craned out. They're about 20 tons for the small ones, and I think almost 40 tons for the large ones. And basically, they have 2 cranes. As you can see there, one crane is holding the other piece in place, and then a pin is just slid into that little piece right there on either side, which you can see there. So at the moment, all of the mini pavilions are done as of last week, and 4 of the 11 arches are done on the main pavilion. Luckily, at one point, the client asked us to put glass over all of these seams. Luckily, that was taken out of the project for budget reasons, which I was kind of counting on. It was kind of painful for me to design it, so I was really happy when they took it out. Because I was like, look, if you really want people to celebrate rain, you provide a certain amount of coverage, but if there's a 4-inch gap in the ceiling and rain is coming through and you have these 30-foot tall openings on either side that wind is blowing rain in, you're going to get wet, and it's okay. And then there's a series of small oculi that are 1 inch to 2 inches in diameter, that because each one is normal to the surface, as the sun moves around, they only light up for a couple of minutes until the sun is at an angle that they are at the wrong angle. So you get these kind of small little dots of light appearing and disappearing throughout the day on the surface of the ground. Okay, a couple images of what we're doing. Probably all of you know what we're doing more than me at this point. You've all been watching it out the windows or doing it yourself. So thank you to all of the students who worked on the project again, and specifically to the students who worked on the renderings here. It's just amazing to see these things pop up on my screen from in California. So I'm really excited about bringing this to the celebration, the Bicentennial celebration, and I encourage you, if you haven't been involved, I'm sure there will be opportunities to be involved. And again, I thank all of you for listening to this very long lecture as well as helping out in this great project. Thank you.
I know it's been long, and we're going to have a reception out on the North Terrace. I'm going to kind of take a vote. Do you guys want to open it up for a couple of questions, or should we move the conversation? Does anybody have a burning question they'd like
You can also ask me outside a burning question. I'm sorry they were so long.
Okay, I think we'll just move it to the reception on the terrace then, and thank you, Andrew. Great.
Sorry about that. This is the first time it is a new lecture format, so
Yeah.
it's like,
It's fantastic. It's great to see the project. Texas coming through.
no, that small little restaurant I did in San Francisco, I just showed that one image of. That's like the only permanent project I've done. I guess the frac is permanent too, but to go from that to that, it's just such. It's a good first project. You know.
So what happened, the pieces that you did for the Champagne company, is that